Hello scholars, welcome back. Mr. Hinkle here to talk to you about how are we measuring our Earth system? How do we measure the hydrosphere, the geosphere, the biosphere, the atmosphere, the exosphere, the cryosphere, the anthroposphere? Well, we measure them through geography and time. Excuse me. The Earth is big, geographically big. The Earth is old, about 4.5 billion years old. So we can hone in on different spatial scales and different time scales to understand varying resolutions for forcing events and feedbacks that have happened, interactions amongst our spheres through geologic time right from the very beginning of Earth itself. Okay, first thing we want to talk about for geography are global effects. And our example here is the evolution of vascular plants 420 million years ago. That's a long time ago. And how do we know that? My favorite question. The rocks tell us, because suddenly we see vascular plants inside of the rock record. We also can, from rocks and cores of the Earth, sediment cores, ice cores, rock cores, piece together the paleoclimate, the ancient climate of Earth. And what we see is, with the evolution of xylem and phloem in vascular plants, there was a global cooling that led to a mass extinction. But vascular plants survived. It's usually what happens in these things. You have some forcing event, in this case vascular plants, that led to a significant amount of oxygenation in the atmosphere, which changed the temperature, which upset all the species, upset meaning it killed them, all the species that had evolved to those certain environmental conditions, leading to a global effect. Certain things are global currently. We call it global climate change, global warming, because it's experienced pretty much everywhere on the Earth. Regional effects are when certain effects are experienced differently in different locations. So we really see regional effects by the distribution of species diversity across the globe. Warmer, wetter at the equator, colder, drier at the poles. In fact, they're deserts. They're just not hot deserts, they're cold deserts. This biodiversity gradient has changed through time, expressing the regional diversity. We also see regional diversity along coastlines. The coast, it's so beautiful. The beach is nice, and it's always cool. It's cool, yeah, right? But it's much like temperature cooler than it is when you are on the interior. So there's Baco, up above it, that 95, that is Fresno. When it's 95 in Fresno, you could drive over to the coast, you could come down to Oxnard or Lompoc, it's 57, 70 degrees. Hey, that doesn't sound so bad. Beat the 90s, get to the 60s. Well, what's going on here is a regional variation for various reasons that have to do with Earth's spheres. The interaction of the hydrosphere and the geosphere. Water has a high heat capacity. Land has a low heat capacity. Land heats up in the day and it cools off at night, where the coasts stay pretty moderate, pretty temperate all year round. Local effects. So local effects can be when one side of the mountain range has snow and the other is dry. This is called the rain shadow effect. Here we can see there's trees inside of the drainage and not on top of the ridge because it's dry and there's more water here. This can be slope and aspect. South-facing slopes are going to have different types of vegetation than north-facing slopes because of the amount of sunlight that they're receiving. So when we're thinking about geography, there's local effects. Now, these don't happen in isolation, just like Earth's spheres don't operate in isolation, but we can look at these varying scales of measurement to understand the spheres' interactions, these feedbacks and forcing mechanisms that are occurring through the different scales of resolution. So this is a tool. This is how do we measure Earth systems interactions? Well, we measure it globally, regionally, and locally. We measure it through time. So we can measure it on the daily, and something on the daily that jumps out is daily temperature, is daily tides. Most species are connected to the diurnal cycle, the sunny in the day, dark at night. And then that's connected to seasons, which is going to be a whole nother scale of measurements. Seasons are going to occur annually every. Winter is winter, and then a year later it's winter again. So this is going to happen annually. The Earth system is measured in years, but events might happen over the course of a year, volcanoes, earthquakes, but we measure these larger events over millions of years. This is geologic time. Geologists don't think in terms of days, weeks, months. No, we think in terms of millions of years, to hundreds of millions of years, to billions of years, which it's hard to fathom. Check out my geologic time lecture on the geologic time scale and think about all those pieces of paper. You got to see it. Check it out. Anyways, so we're also thinking in terms of millions of years as one of our scales of time, because the Earth, 4.56 billion years old, that's a long time. It's unfathomable, but we have calculated it. So we have measurements through our two scales, space and time. And we need a baseline. We take 150 years of weather data and we chunk it and we figure out a norm. Based on everything that we've seen, all of the data, here's the norm, and here are anomalies from the norm, departures from that normal behavior. We're taking information that has been recorded, and we're using that as baseline normal conditions and comparing departures from that norm to understand what's happening currently and what may be happening in the future. Again, the big one here is global climate change. We're thinking, is the climate changing? How is the climate changing? Why is the climate changing? What the heck is going on? But we've been measuring weather for a long time, since the beginning of the 20th century, and now we've got lots of daily, even century measurements that we can create the norm, and we can look at and we can say, oh, the global average temperatures on Earth have risen significantly compared to our baseline normal set of data, showing us a data anomaly. So these are scale. Now, how do we measure? Well, the how is really answered in multiple ways. Direct measurements and satellite measurements. That's basically what we got going on here. So direct measurements are going to be ground-based instrumentation. I love it. There is a scientist climbing up here. Where's his hard hat? I don't know, but I like what he's got going on. This is a meteorology station at the Devil's Postpile, which is rad. It's in Mammoth. It's cool. Go visit. You won't be upset that you did. These produce the highest resolution data because they're directly measuring what's going on. There are satellites all around our Earth, and it's awesome. It's amazing what satellite information can do. Every person benefits from satellites. If you've ever used your phone to go anywhere, you've been plugged into global positioning system information that is coming from the satellites. And the satellites can give us remote sensing, and they measure everything. Sea surface elevations, temperature, carbon dioxide, water vapor, the list goes on and on and on and on and on, more things than I can even count. And these satellites produce a lower resolution, but a greater distribution of information. So the goal here is to have your satellite coverage to giving you the full view, and then to use direct measurements to refine your satellite information and to help adjust the equipment so that it can make more accurate viewings of what's happening here on the surface of Earth. Remote sensing, expensive, difficult to develop, maintain, having these things up there. Ground-based instrumentation, it's not as expensive, but you need people to do it. So NASA, the national administration, the national atmospheric, oh my gosh, I just blanked what NASA stands for. Wow, how did I do that? National Aeronautical and Space Association. This has got to be it. National Aeronautics and Space Administration. Who would have thought? Not to be confused with the National Oceanic and Atmospheric Association, NOAA. NASA, the National Aeronautics and Space Administration. Okay, got it. Glad we could connect on that. Does really cool things. They're out there observing space, and from space, observing Earth. And right now there's a series of satellites called the Earth Observing System, the EOS, that focuses on studying every sphere of the Earth system. So who's studying the Earth system? NASA. And they're doing it through the Earth Observing System. Thank you, NASA, for helping us understand this home of ours, the planet Earth, and all of the intricacies in the complex set of interactions that are happening every single day. Not only that, but we're also measuring space weather in the exosphere because the sun generates wind, solar wind, and that solar wind is dangerous. Fortunately for us, we have a magnetic field. The center of our Earth is solid iron. It's a huge magnet in the middle of our Earth, creating a magnetic field, and that magnetic field deflects solar winds around us, keeping us safe on Earth. Mars once had an atmosphere, and there's evidence of plate tectonics, volcanism, rivers, water, but none of that exists anymore, likely because it no longer has that magnetic field to protect itself. So we're out there measuring space weather, we're measuring Earth weather, we're trying to get a comprehensive understanding. Let's go to the conclusion. We're trying to get a comprehensive understanding of what's happening on Earth, within the Earth system, the interactions of the Earth spheres through the scales of measurement, space being geography, global, regional, local, and time on the daily, the annual, the millions of years in Earth, on Earth, and from space, so that we can know ourselves and we can know our Earth. Thank you so much. I'll see you again.